Hi, welcome to the Calculus 2 lecture series. And this is unit number 2. We talk about the techniques of integration. And this will be our last lecture for this unit. We are going to talk about the improper integrals. This is the second video for this lecture. So on the first video, we introduced the different type of the improper integrals. Right, so we talk about what is type 1 improper integrals and what is type 2 improper integrals. And so for this video, we are just going to try to practice some example to see how do we do that. Okay, so now let's go ahead and go to our lecture notes here. Okay, so this is what we did from the previous video. So we talk about the type 1 and the type 2, and then we kind of did a simple example to identify the type 1 and the type 2s here. Okay, so now we are going to take a look at some examples here. So let me, before we do it, let me kind of erase here. I want to put some notes here. And those are the kind of some rules we need to know. All right, so in here, okay, so let's go ahead and start. Okay, so in here, I want to put a few rules here before we try to do the experiments here. So I think most of you knows here. So if you have a fraction, if the numerator is some constant, right? So if the bottom of your fractions become, that means I put this like, that means approach to infinity. That means the bottom, the denominator of your fraction become very, very big and become infinity, then this fraction will have the value 0. I think most of you know, but I just want to refresh your memory. And then the other ones here, if you have a constants here, right? So if the bottom of your denominator, and so here still is approach to zeros here, then these ones here, we're going to approach to what? We're going to approach to infinities, right? So it become very, very big. And then the same things here, all right? So if I have some infinity, so if a numerator, I approach to infinity, and I have the denominator is a constant, then this one will be what? Will just be infinity. And the other things here, if your denominator is a constant, if your numerator approach to 0, right? Then this ones here will be what? Will be 0. We learned this in our calculus 1 when we talk about the limit. Then if in here, so we know the infinity over infinity. So if you have this one's here, this is undetermined. So it's just the same thing for the 0 approach to zeros, right? So this is undetermined. Then we might need to use the L'Hopital's rule to do that. But so for here, those are the couple of things we need to be careful, right? So to see if this integration exists or not. All right, so now let's start here. Okay, so the first one here, I want to do the integration for 1 to infinity, 1 over x cubed, right? So this is the type 1, the improper integration because I have infinities there, right? So just like we did before, so this one will be equal to the limit t approach to infinity. Then you have 1 over t, then 1 over x cubed, 1 over x cubed dx, right? So 1 over x cubed is x to the -3. So by the power rule, so the integration will be pretty simple. So this is a t approach to infinity. And then you will have integrations here. So this is -2, right? X to the -2. Then you have t to 1. So you can simplify this. This is t to the infinity. So this will be -2, and then this is x to the what squares, right? So if you like, you can put this negative right to the top. That's fine, and then you have so yes, you can put it into the top, and then this is -1. Then you have the t and the 1 here, right? Then just like you substitute the upper bound, so this is t approach to infinity. So when you substitute the upper bound, what you will have? You will have -1, 2 to the what? T square. And then you substitute the lower bound, right? So the lower bound, when you substitute here, will be the -1 to the 2 here. So take a look here, right? So these ones here, when the t go to the infinity, this number will approach to infinity. So this value will approach to what? Will approach to 0, and then this is a constant. Don't forget negative and negative is a positive, right? So what is the final answer? The final answer is 1/2 here. Okay. All right. So now let's take a look at this one. It's kind of just review about what we learned in the in the integration formula. Okay, secant square x is from 0 to pi/2. I know the secant is the reciprocal of cosines, right? So cosine is like these ones here. So when the cosine at the pi/2 is 0, so secant at the pi/2 is what? It's not defined, right? So what type of the improper integrals here we have? We have here is what? Is the type 2 kind, right? So that means that means this second function is not continuous at the pi/2. Okay, so now we can do here. So we said this is the limit t approach to the pi/2. Now let's see, we are approaching to from right hand side or left hand side. So this is 0, this is pi/2. Because it's not so it's a parenthesis, so we approach it from the left hand side, right? So that's why I approach to pi/2 from where? From the left hand side. Got that? Okay, now here this is 0t. Then you say the secant square x dx here. So the secant square x dx, so this will be the t approach to the pi/2 from the left hand side. And then the secant square, oh, that's pretty good. That is the tangent x. Then have 0 to t, right? So now you will have a limit t approach to the pi/2 from the left hand side. So you will have a tangent t minus the tangent 0, correct? Okay, so now let's take a look at the tangent 0. This is equal to 0. Tangent t from the left hand side. So I know the tangent function is like this, right? So this is a tangent. So when you approach from the left hand side, then what happens here? What is the tangent t value going to approach to? So this will approach to what is infinity, right? So this is the infinity minus 0. So what is here? This is infinity. So this integration is what? Is divergent, right? Because it doesn't have a value, that's not integrated to a fixed numbers here. All right, so now let's take a look at this one here. So we have 1 to the infinity, x to the e to the x square. So this basically is x and the e to the x square dx, right? So we know it's it's everywhere, it's continuous everywhere from 1 to infinity. So for this problems here, what type of the integrations with the improper integration we have is a type 1s here, right? So because I have the infinities there. So in order to do this, I think you should be very familiar with right now. You have x squared. So what I need to do, I need to use u sub, right? So I will say u is equal to the x squared. Then du is equal to the 2x dx And in here, you only have x dx. So I need to adjust the constant. So I will say du over 2, this is x dx here, right? So then the whole distance here going to be, so this one's here going to be integrating the 1/2 e, the negative u du's here. Okay, so the, or maybe here instead of negative, let's put the u is equal to the negative x, and this is negative x, this is so negative put it in here, so this is positive, so this is negative 1/2. I assume you know how to do this very well. So okay, so this one's here, this will be the limit t approach to infinities, right? Then you have 1 over t x to the e, the negative x squared dx. So by the u substitutions here, I know this will be limit t approach to the infinity. And then in here, this one, after you do the u sub, you will get this is negative 1/2 and e to the negative x squared. And then you put your upper bound, lower bounds here, all right? So now let's take a look. This is limit t approach to infinity. So up bound will be negative 1/2 e to the negative t squared minus the lower bound 1/2 then e to the negative what? Negative 1s, right? Okay, so now let's take a look at these ones here. These terms here, this term really is 1 over e to the t squared. So the t approach to infinity, then this term approach to infinity. So the whole things here approach to what? Approach to zeros, right? Then positive, negative is positive. So the final answer for these ones here is the 1/2 e to the negative 1, or you can say 1/2 e here. Okay. All right, so now let's take a look at this one's here. This is 1 to infinity pi over x squared, because the x squared is only discontinuous at 0, but the integration range does not include 0. So we know is, the integratable, all this is continuous at all these intervals. So this is a type 1. We have infinity there. Okay, so now let's take a look again. So this will be the limit t approach to infinity, 1 over t and the pi, the x squared dx. So this is x to the negative 2s, right? So then you will see here, this is limit t approach to the infinity. And then this is negative 1 times the x over 1, then pi here. Then you have a t and 1, correct? All right. So now you can put this negative 1 on the top. So this will be t approach to infinity. So you will have the negative pi over t, correct? And then minus, and this is minus pi over 1. All right, and then here again, here, right? So because the t is approach to infinity, so all these things approach to what? Approach to 0. And then this is negative. What you have here is a positive, right? So it's a pi here, right? So that is why we introduce here, be careful, right? So when the denominator approach to infinity, approach to 0, denominator approach to 0 is to infinity. Okay, so what is we call this a comparison test here, right? So the comparison test is basically you compare two functions here. So suppose here, I say, it's kind of intuitively true also. So suppose I have, like the gx is all positive, and then the f of x here. So every, so for all the x greater than equal to a, so that means f of x is greater than gx for all the things in domain. So now if I know if you integrate from a to the infinity, f of x dx, okay? If this one is a convergent, that means when you integrate this one, is come to a fixed number, it's a convergent. Because gx is less than f of x, so I know what happens here. So I know the a to the infinity of the gx dx has to be what? Has to be convergent. It's kind of like intuitively true, right? Because every f of x is greater than gx. So when the f of x integrate to the infinity, then gx definitely is a convergence here, right? So that's why it's a convergent, then the f of x is bigger. So on the other side, it's the same things here, right? So if in here, okay, if so now if you know the so same things here, if there's okay, so if the still the gx f of x is still greater than gx for all the x greater than equal to a here. Okay, so now if you integrate, okay, so if you integrate like in here, if you say the a to the infinity of the gx here dx, if this one is a divergence here, okay, because gx is less than f of x, right? If the gx is a divergence, then what you can conclude about the f of x, because f of x is bigger than gx. So of course, the what here, so then the f of x dx is a what? This one is a convergence also, right? So if you have a function greater than, you know, like gx is a function less than f of x. So if this one come to the number of infinity, then of course this one come to the number of infinity. So the same way is here, because f of x is bigger. If fx converge, then gx has to converge here, right? Okay, now let's take a look here. So the problem number 3, let's say, let's show this is 1 to infinity sine x over x squared is a convergence here. If you really physically want to carry out this integration, probably is very difficult. All right, so that's why we said, but in here, they only want us to see is it convergence or not. So maybe you said, oh, maybe I can use the comparison series here, especially if you see a trig functions here, right? So my integrations here, be careful here, my integration region is 1 to infinity. So I know the sine x, right? So what we learned about the sine x, we said sine x is always between -1 and 1, right? But this is the absolute value. So that means the sine x always between 1 and 0. Doesn't matter what values, right? So this is for what? For all the x from 1 to infinities, right? Okay, so now let's see here, because this one, then let's see, now I'm dividing the x squared, all the terms x squared. Okay, so what I have here, so this one here is 0, and then this is sine x squared is less than 1 over x squared, correct? And now I'm taking the integrations. Okay, so I'm taking the integration for all the side from the 1 to infinity, 1 to infinity, 1 to infinity. Of course, this one is 0. Okay, so now let's take a look here. So integration from 1 to infinity, 1 over x squared dx. So this is a type 1. So I would say it's the limit t approach to infinity, 1 over t, right? So this is 1 over x squared dx, right? So x squared, 1 over x squared is extra -2. So when you integrate that, This will be t to the infinity, so will be the x negative 1 for the t to 1. Am I right? All right, so this will be a t to 1 here, right? So now in here, now you put the limit to the t to the infinity, and then in here you will have the negative 1 to the t minus 1 over 1. Be careful about the negatives, right? So in here the same thing, so because this is go to infinity, so the whole thing go to 0. Then negative get you what? Get you positives, right? So what is the final answers here? The final answer is 1. So I know this is a convergence. Because this is a convergence here, so I know the 1 to infinity, the sign x squared dx converge. I don't really know what is converged to, but I know it's a convergence between the values, what? Between the values 0 and 1, right? Because here, this is 0, this is 1. So I know this function has to be converged to some value between 0 and 1 here. All right, that's it. That's it for the DC improper integrals. I guess this one is pretty easy. The only thing is you just need to be careful, right? So when you have the problems here, you need to know it's type 1, type 2. And then sometimes you need to break it into 2 parts to take care of that discontinuity points. All right, that's it. And we finish this unit. That's great. So the next thing, so we're going to talk about some simple applications about integration again. All right, so nice talk to you and looking forward to talk to you in our next topic. All right, bye.